All right, everyone, welcome back to the online fractional calculus seminar series. We're starting again for 2025, and the first speaker of this year is Professor Zivorad Tomovski, currently a full-time professor of applied analysis and probability at the Department of Mathematical Analysis and Applications of Mathematics, Faculty of Sciences, Palacky University, Olomouc, Czech Republic. His PhD was conducted in 2000 under the direction of Professor Telyakovski of the Steklov Mathematical Institute, Moscow, in the area of approximation theory and Fourier analysis. He received the PhD degree at the Faculty of Mathematics and Natural Sciences, Cyril and Methodius University, Skopje in 2000, where in 2010 he received a full professorship position, and in 2012 he was awarded Best Scientist. In 2022, he received habilitation in applied mathematics at Ostrava University. His recent research has been focused on the development and the analysis of computational tools for mathematical modeling of anomalous diffusion, wave propagation, and fractional PDE with stochastic analysis. He has published more than 100 papers in international journals of mathematics and physics with impact factor, and 2 Springer monographs available online from his ResearchGate profile. Professor Tomovski has been a principal investigator or co-investigator in numerous international research projects and grants supported by DAAD Germany, NWO Holland, Einstein Foundation Research Program Berlin, Austrian Agency for Research, Croatian Ministry of Sciences and Sports, Macedonian Ministry of Science and Education, Marie Curie Program, and bilateral grant GACR DFG. Today, we are happy to hear him give his presentation about some analytical inequalities in fractional calculus. Please go ahead. The floor is yours.
Thank you very much for introducing myself. I decided to speak about some inequalities in fractional calculus. This talk is connected with my published book 2 years ago in collaboration with Professor Josip Pečarić and Said Iqbal, where we took some special results of this book. My presentation today will be divided in 4 parts. The first one, we will present some inequalities for Mittag-Leffler functions. The second part, inequalities for fractional moment generating function in probability theory. The third part of the talk will be connected with the fractional derivatives of trigonometrical series, some inequalities, and approximation in L1 LP space. And finally, I will present some open problems concerning the part 3 and also the references which are used during my presentation. Firstly, I will give some elementary definitions of subadditive and superadditive functions. If A and B are subset of the set of real numbers, then the map function f of A to B we will call to be subadditive if for all x and y belongs to the set A, the following inequality f of x plus y less than or equal to f of x plus f of y is satisfied. Also, for converse inequality, the function f of A to B is called superadditive for all x, y which belongs to A. Some examples, for example, the function x squared is superadditive function, and also x power function p, when p belongs is greater than 1, are examples of superadditive functions. When we consider the power to be half, then we obtain this root function, which is a subadditive function for x and y non-negative numbers. and also when p generally is between 0 and 1, for x and y non-negative, then x plus y power p is less than x power p plus y power p. The functions root of x and x power p for p between 0 and 1 are subadditive function examples. We ask of which type the Mittag-Leffler function defined by 1. It is series expansion. It is analytical function in the complex plane, and this parameter alpha real part is greater, but we will consider this function to be with real variable. Thus, this function is subadditive or superadditive function. It's interesting question. We will present this by analysis of the definitions for superadditive and subadditive functions. I will mention the Jumery results, which is published in 2009 in Applied Mathematics Letters. He proved this proof, but did not prove inequality 2. It is identity, it is not inequality. He proved that for alpha between 0 and less or equal to 1, this convolutional relation identity for Mittag-Leffler function when alpha is between 0 and 1. But this is not true. He applied this identity to define inverse Fourier transform, but this identity is wrong because it holds only for alpha equal to 1 or for only exponential function. Exponential x plus y is equal to product of a power x, a power y, and so we can conclude that for alpha different than 1, this identity does not hold. But it's interesting that for this Mittag-Leffler function, there holds inequalities, very nice inequalities, by application of the definition for superadditive and subadditive. We can conclude that this Mittag-Leffler function for alpha between 0 and 1 is subadditive, and for alpha greater than 1, it is superadditive function, but for x and y to be non-negative real numbers. The inequalities, these inequalities 5 and 6 are strict for x and y to be positive. The proof of these inequalities are given by Gerhold and Simon in 2023. They apply the definition for superadditive and subadditive function, but by proving that logarithmic of Mittag-Leffler function of x power alpha, that is a log convex and log concave function, and by application of the definition, it can be easily proved that these inequalities holds true. So Jumery results is incorrect, and his method for defining inverse Laplace or inverse Fourier transform is not good. And these inequalities 5 and 6 we applied to give some property for the moment generating function. So in the probability theory, we define characteristics and moment generating functions in collaboration with Metzler and Gerhold in the journal Fractional Calculus and Applied Analysis in 2022. So by introducing Mittag-Leffler function with parameter alpha, because for alpha equal to 1, it is the classical definition for generating function, moment generating function for the random variable x of continuous type. And also for the characteristic function, we put imaginary unit in the Mittag-Leffler function, so we define to be its complex function, and P of x is probability density function. So by application of the inequalities by Gerhold and Simon, we prove this theorem. If x and y be non-negative independent random variables and t is non-negative real number, then inequalities 7 and 8 holds true for the sum and for the product of the Mittag-Leffler function of the moment generating function. The proof is very elegant and short. So when alpha is between 0 and 1, if we use the inequality of Simon and Gerhold, we can apply mathematical expectation of this Mittag-Leffler function with the variables t power 1 over alpha x plus t power 1 over alpha times y power alpha. So we can apply that the function is subadditive function, and we get this mathematical expectation. And if we use that x and y are independent random variables, we can separate these mathematical expectations of both Mittag-Leffler functions, and we obtain our result. The same method can be applied also if we use a complex, but under another conditions we need. But here we work in the real line, so it's easy to apply this analytical inequalities for Mittag-Leffler function. The next part of my talk is connected with the trigonometrical series, some inequalities in trigonometrical series, and its estimations or convergence of the fractional derivatives of the trigonometrical function. We know that the Dirichlet-Kerbel in Fourier analysis is defined by relation 9, and that the Riemann integral of this kernel in the interval minus p to p is equal to 1. But the L1 norm of this Dirichlet kernel is not convergent, but it can be asymptotically approximated with 4 over p square logarithmic n when n is large. This estimation is applied in many theorems to analyze L1 integrability and convergence of trigonometrical series. For example, Sidon in 1939 for bounded sequences alpha key from key 0 to n proved this 11 inequality for the linear combination of the Dirichlet kernel. So if alpha key are bounded, then he give analytical method. By analytical method, he give very elegant proof of this Sidon inequality, which is applicable in approximation theory of trigonometrical series. The constant 2 is the best possible in this inequality, and the method is which is used to prove 11 is to separate the integral on the left side in the sum of two integral of 0 to p over n plus the second integral from p over n to p because of the singularity of the Dirichlet kernel. And in the first time there is applied a Cauchy-Bunyakovsky-Schwarz inequality or Parseval identity. And in the second integral, it's applied uniform bounding of the Dirichlet kernel, and the elegance of the inequality 11 comes very easy. I will mention some special classes of sequences of real numbers. We know that the sequences AN is called convex if the second difference is non-negative. The sequences AN is quasi-convex if this series is convergent, sum of n plus 1 time absolute value of the second differences, this series is convergent. If we suppose that AN is convex, then the convergence of the series 2 is obvious, because by application of Abel summation by parts of the series, it's easy to prove that this series is convergent. So the class of the quasi-convex sequences are a wider class of the class of convex sequences. If we suppose that the sum of the first difference of the sequences AN absolute value is convergent, then we call that AN is of bounded variation. It's a sequences of bounded variation. There are many theorems connected with the convergence of trigonometric series with special coefficients. When the sequences is for example, quasi-convex, or if the sequences AN is monotone sequences, or increasing or decreasing, and it's obvious that if AN are monotone sequences, then it follows that these sequences is of bounded variation. I will mention three important results concerning the convergence of the trigonometric series with convex coefficients. The first result is proved by Young in 1913, and later this theorem is generalized by Kolmogorov in 1923 for the trigonometric series with quasi-convex coefficients. After 41 years, Telyakovskii proved very elegant inequality 12 for cosine trigonometric series with quasi-convex coefficients. He proved this inequality. He supposed if AN are quasi-convex, then the integral of the cosine trigonometric series is less than of this series. This theorem is published in 1964 in one Russian journal, Mathematical Notes, and I leave it for the reader to consider if are interested for the details of the proof. But interesting class of which are wider of the class of the quasi-convexes is the class of S. Class S of the sequences of real numbers, defined by Telyakovskii in 1973 in Mathematical Notes. The class S is equal to the set of all positive sequences AN which tends to 0, such that there exist capital AN and new sequences positive, which is convergent to 0, decreasing, and this absolute value inequality is satisfied. The first difference of AN is absolute value is less than of the new sequences, and the series of the new sequences is convergent. Telyakovskii defined these sequences, which is a wider class than the class of quasi-convex sequences, and analyzes the convergence and integrability of 14 and 15 cosine and sine series. The first important theorem proved by Telyakovskii is if we suppose that the sequences an belongs to S, then the cosine series is Fourier series of some function f which belongs to L1 on the interval 0p, and there exists the positive constancy such that this inequality holds true. Moreover, the norm of the partial sum of the cosine series is convergent to the function f of L1 if and only if an times logarithm of n tends to 0. The proof of this theorem is based on the theorem by Sidon. Separation of the integral on two parts, and application of the Abel transformation by summation by series, where will be appear a Dirichlet series, and then application of Sidon inequality. Zygmunt, we will mention the Zygmunt inequality about the trigonometrical polynomials. In 1959, in his book, presented this inequality for the first derivative and for the norm p larger than or equal to 1. If Tn is a trigonometrical polynomials, then norm under LP norm of the first derivative of this norm is less than n times the norm of the trigonometrical series in P norm. The proof is given in the book by Zygmunt, published in 1959. I think that first version of the book is in Russian. I have Russian version, but there is also translation in English. The suitable fractional derivative operator, which works with trigonometrical functions, sine and cosine, and trigonometrical polynomials, is Weyl fractional derivative, which is of Riemann-Liouville type. The derivative, the definition of this operator is given by the integral 17, where the derivative first derivative is given before the integration, and the borders of integration are from x to infinity. This is the difference of the Riemann-Liouville definition, because we have there from 0 to x, but now we apply this integral to be from x to infinity, where x is a real number, and gamma is gamma function where alpha is strongly less than 1 and alpha is non-negative parameter, order of derivative. By application of the Zygmunt inequality for trigonometrical polynomials, which is called Bernstein inequality in practice, we generalized this inequality for the Weyl fractional derivative when alpha is between 0 and 1 and p is greater or equal to 1.
Sorry, can I just...
Please?
Sorry, we cannot see the equation 18 because there is a pop-up from Zoom. Could you just click where it says hide? Not stop sharing, click on hide.
Okay, I also
Thank you.
cannot see, but now I can. Sorry. The norm of the Weyl fractional derivative of the trigonometrical polynomial is less than this constant C alpha, which is positive, and times n power alpha. This is alpha is the order of derivative, So for alpha equal to 1, we get the special version of Zygmunt and the norm of the trigonometric times norm of the trigonometrical polynomials with P norm. I present this this inequality, the proof of this inequality, in 2002 in the conference Constructive Functional Theory in Varna in Bulgaria. And by application of this generalization of the Bernstein inequality, I prove also a generalized version of the Sidon type inequality for the fractional derivative of the Dirichlet kernels. Dirichlet kernels is sum of cosine functions here, and this is a trigonometrical polynomial, and we can apply here in the integration Weyl fractional derivative. And by application of the Sidon type inequality and Bernstein type inequality, we obtain this this generalization of the Sidon type inequality given by 90. Let's mention something interesting about L1 and LP convergence of this class S index alpha. Independently, me in 2001 and Laszlo Landler in 2001 in GPAM and in MIA, Mathematical Inequalities and Application, we introduced this class, which is a subclass of the class of Telyakovskii, Sidon Telyakovskii, where we replace the series with this power series n power alpha times an, and we obtain for alpha equal to 0 S alpha to be identical with S. But for alpha strictly positive, we obtain that S alpha is subset or subclass of S. It is interesting and unpublished result to consider some property of this class. For example, when alpha is greater than beta, what is the conditions, the relation between inclusion, how inclusion holds for S alpha and S beta class, or to found S alpha plus beta, S alpha intersection S beta. I don't know, some very popular properties of the sequences, classes of sequences, and how can be applied for next investigations in the approximation theory by trigonometrical series. It's an interesting question for research. I would like also to present two inequality concerning the fractional derivative of the cosine and sine series when the coefficients of the cosine and sine series belongs to this class S alpha, when alpha is non-negative and less than 1. By introducing this parameter alpha in the class of Telyakovskii, it helped us to formulate theorem for the integrability of the fractional derivative of cosine and sine series in the space L1 of 0 to p. So if the coefficients belongs to S alpha, then the fractional derivative of cosine series is a Fourier series of some function which is differentiable in the sense of Weyl fractional derivative and belongs to L1 from 0 to p, and this inequality holds true, where C alpha is constant, which depends of alpha. The strong inequality, but from the interval starting from P over mi plus 1 is given for sine trigonometrical series when the coefficients belongs to the same class, and for all m integer number 1, 2, 3, starting from the integral of P over m plus 1 of the fractional derivative of sine series of order alpha is less than C coefficient C alpha times this partial sum of n power alpha minus 1 times absolute value of an, and plus this series which is convergent because the sequences an belongs to the class S alpha. And how we will get from here the estimation for the integral starting from 0 to P. It's easy. If we suppose that this series is convergent under the same parameter, then, and letting m tends to infinity, then this the border will be 0, and the integral will be from 0 to P, and the right side will be changed the partial sum with the infinity series. So we obtain this corollary of the previous results. If the series is convergent, then fractional derivative of sine series is a Fourier series of some function which is fractional derivative exists of g in L1 0 to P, and this integral holds true. Interesting question is how we can investigate similar inequalities for fractional derivatives, but for the L1 half space. So for the LP space, but with fractional power and less than 1. So I formulate open problem, find necessary and sufficient conditions for L1 for L half convergence of the fractional derivatives in Weyl sense of the series 14 and 15. Or a general question, consider the problem in general space LP 0P when P is between 0 and 1. This is open problem for the fractional case of the previous results. I have some idea, but if something of you which listen my talk today is interested, we can prepare paper about the continuation of these results. So thank you for your attention. Just to mention some references. There is the first references I just mentioned that's published in Fractional Calculus and Applied Analysis in collaboration with Metzler and Gerhold. And I will mention also some of my papers published very long time ago, 24 years ago, in mathematical inequalities journals. There I'm a single author, published in conference in Romania in Timișoara, 2001. Also in Journal of Inequalities Pure and Applied Mathematics, it's Australian journal, electronic journal. One of the paper is published in the special proceedings of the conference in Varna, published in Darba Sofia, 2003. The 7 references is Zygmunt book, Trigonometrical Series, volume 2. 8 paper is the paper of Telyakovskii, published in 1973, about the convergence and integrability of the trigonometrical series by Sidon Telyakovski class S. And finally, the paper of Lindler, on the utility of the Telyakovskii class, published in 2001, where he also defined this class as alpha and gives some interesting inclusion between some classes. So I can close my lecture. I prepare this material for today. Hope we will meet again next time. If you have any question, I am open to discuss.
Thank you very much for the presentation. Do we have any questions from the audience? You can raise your hand or you can simply unmute and ask questions or comments.
I cannot see every of you. I don't know what to do to see your faces because I only look on my presentation.
Maybe if you press the escape button, you can go out of the full
Okay.
screen mode.
Escape, and then, okay. Thank you.
Any questions, anyone?
Yes, I just technical question.
Yes.
Please.
Please, if you can go to page 13.
13 page.
Yeah, number 13. This is two theorems.
Okay.
Yeah, this
Yes.
is, yes.
Okay.
Yeah, just technical question. I just want to see the relation between the first estimation and the second one. Is there, you are splitting the integral 0 pi to 2 integral to get the second result of the theorem?
No, the proofs of both theorems are independent.
I see.
In the first estimation, I use Dirichlet kernel, but
Okay.
for the sine series, I use conjugate Dirichlet kernel.
Okay, thank you.
Conjugate Dirichlet kernel is more complicated. And for these kernels are satisfied different estimations.
I see. Okay, thank you.
And because it has singularity, it's not possible to integrate from 0, because at the point 0, the conjugate Dirichlet series have singularity, and I started from p over n plus 1, but in the corollary, in the next results, I reduced this theorem to holds from 0 to p under satisfying the convergence of the series.
Yeah,
Thank you.
You're welcome. And for the Mittag-Leffler subadditive, superadditive, is that true for multiple variable or just for single variable?
It's not interesting question. Maybe there are many properties, and for you think for the second, for two parameter Mittag-Leffler,
Yes.
for Prabhakar Mittag-Leffler.
Yeah.
This is your question.
Yes.
But to analyze, maybe it's open question. I don't know. I have not met to analyze the subadditivity and superadditivity
Thank you.
for the more parametric Mittag-Leffler functions.
Okay, thank you.
I don't know if it is interesting.
Thanks.
Thank you. Actually, I had a question also related to these subadditive and superadditive results. Have
Good.
you used these results in your analysis in the later work? Is there a connection between these Mittag-Leffler results and the results on trigonometric series?
Good. Your question is if it is possible to analyze for the trigonometrical series?
No, I'm asking, you presented some results related to Mittag-Leffler and...
Yes, I I said that I will present two different fields. They have not connections.
Okay.
Just I selected interesting for me topics from the book published with Pecherich and Site-Iqbal. And I selected these two fields and compose my talk of analytical inequalities in fractional calculus.
Okay, I understand. Thank you.
Thank you.
Any other questions, comments? No, nobody else? All right, then once again, we thank Professor Zivorad Tomovski for his talk, and I will stop the recording there for the first talk.